Okay, then everybody, we might as well get started. Hello, thank you for coming. My name is Matt, and today I'm going to talk to you about writing allocation-free code in C#. This is a topic which has kind of got a bit trendy lately. There's a lot of people talking about it. There's a lot of mention on it in the blog posts and what have you for .NET Core, and it's a good way of kind of improving your performance by reducing the amount of memory that you allocate. And so I'm going to have a look at a few things. We're going to look at some stuff which is perhaps sort of micro-optimizations and some other things which are a bit bigger, a bit more interesting, such as the use of the new Span&lt type and the APIs around that. But we're going to start off with a little bit of simple advice for how you can write some allocation-free code in C#, and that is don't do it. The things I'm going to show you today, don't bother. Most likely, you don't need to do this. These are going to be some low-level optimizations and micro-optimizations, and basically you're not going to need it. Unless, of course, you actually do need to do this. And I can't tell you whether or not you are going to actually need this. So basically, if you take one thing away from this talk, it's this one. Always be measuring, profile. If you need to do this, you will know. You will see in your profiling results that you need to do this. You need to do something about performance, and there are things you can do that then to reduce performance by reducing the number of allocations you've got. But always, please be measuring. Don't just do it on gut feel. Measure, make sure you know what you're doing and why you're doing it. So let's talk about why. Why would you want to write allocation-free code? Reduce the number of allocations you've got. We've been using .NET for a good while now, and we understand that we've got a managed memory environment, which is great. It does a lot of work for us, and it removes the need to sort of manually handle our allocations and when we free our memory there. And so we've kind of got it into our heads, really, that managed memory is cheap. This isn't strictly true. It's more along the lines that allocation is cheap. So it's very easy to allocate memory, but it's garbage collection then that is expensive. So garbage collection itself, it stops the world, it pauses everything. It has to do a lot of work then to clear everything up, compact your memory down, and it introduces pauses. And so that's really what this is all about here. It's all about throughput. And it's about the idea as well that you might not be using a lot of memory, but you might be allocating and freeing a lot of memory. So your memory traffic might be very high. You might be using 5 gigabytes of memory over time, but your peak memory could sort of stay at about 500 megabytes. And it's about trying to reduce this throughput. So if we're talking about throughput, the idea is that more allocations mean that you have more garbage collections. More garbage collections mean more pauses, and pauses then disrupt the throughput. And if we try and improve our throughput then, this gives us a smoother experience. Not necessarily faster, but it usually does equate to the two, but we are smoother. We're having less pauses, less interruptions, and things run smoother, and therefore they're usually faster. So this is good then for anything that is sort of particularly low latency. So servers, you obviously don't want a garbage collection while you're serving a page, because then the user has to wait until the garbage collection is finished before they see the page. The same with games. You don't want to be lining up to take a shot at somebody and everything pauses while there's a garbage collection and then carries on. Similarly with interactive user interfaces, you don't want it to pause there and block it up because you can feel it and it interrupts the flow of what you're doing. And if you look at those lists as well, that kind of covers a lot of the applications that we tend to build. So generally speaking, throughput and improving throughput is a good thing. It's also useful if you are working in a constrained environment. So if you're working on a mobile device, for example, or a console, or other similar sorts of environments. Using less memory is generally, it's a good thing. So if you can be more conservative with your memory, you get, again, reduced garbage collections and better throughput. If you're working on a less powerful device, then your garbage collection can be slower, and also it's doing more work, so it's going to be using up battery. So fewer garbage collections will be better for battery life. And all of this does come down to throughput, and if you think about throughput and games again, mobile devices are absolutely huge. Mobile gaming is absolutely huge on mobile devices. And one of the big environments for writing games on mobile devices is Unity, which is C# based. So all of this does apply. But there's another reason which I think is very useful for understanding all this kind of thing, is that you should know your platform. So even if you're not actually going to be doing this in your own code, you're still going to be using it in the platform itself. So one thing that has sort of changed over recent years with .NET is how performance is really a key part of the design of the platform. It's really built in. So every feature that is now being built, there is always an eye on performance. And you can see this in some of the recent features. So if you are looking at C# tuples, for example, there's already a system.tuple type. They could have just built it around that. But those are reference types. Those would cause allocations every time they get used. So they've actually introduced a new type, value tuple, which is a struct, allocates on the stack. And that is then better then for allocations and, again, for reducing the amount of memory that you're using. You can see a similar sort of thing with the iAsync enumerator feature, which is an await for each. And also in value task, which has been introduced to work with asynchronous programming. I'll talk a bit more about that in a sec. And then, of course, this new Span&lt API, which, again, I'll talk about in a little while. So let's have a look at some easy things here. What are the low-hanging fruit? What are the easy things we can do to reduce the amount of memory that's going on? Just kind of keeping an eye on these things. So again, once we've profiled, we want to have a look at this. We want to make sure that we're doing the appropriate things. But there's a bunch of things we can do which are very easy to sort of fix some of these things. So we can reuse objects. We can have object pooling. We can pass in pre-allocated arrays rather than having to allocate them all the time. Reuse an array once it's finished, rather than having to let the garbage collector clean it up and reallocate new stuff. String concatenation. We all know this one. Use a string builder instead of just concatenating strings there. And if you're using a string builder, you can reuse them as well. So you can combine that with the first one there. And if you know the length of the thing you're trying to build, you can pre-allocate it as well, so it doesn't have to work around reallocating items there. Params is an interesting one. So we'll have a look at that. Params is a good one here because the allocation that happens here is something that you don't necessarily see when you're writing the code. It's something that the compiler is generating for you. So you can be writing code like on the left here, passing in two string variables, two string values, sorry, or nothing at all. And the compiler is actually generating the code on the right. So it's allocating an array for you, allocating an array of two string values here. And even when you're not passing anything at all, the compiler is allocating an array for you. So every time you call, there's another allocation, but it's an allocation for an empty array. Except I'm lying to you. That doesn't happen. On newer frameworks and newer compilers, we use the array of empty, the array.empty of t method here, which will reuse an empty array for you. So it's important to know, again, this is it. You've got a profile. You've got to know what the platform is doing here. You can't just trust me. I'm just some guy standing on a stage. Don't trust me. Profile and see what's actually going on and what's happening. But these kinds of things are allocations happening which you need to work with. So boxing. That's another useful way of reducing the amount of allocations that happen. Boxing happens when you pass a value type to a method that expects a reference type. So you can have something like console write line. The parameters that get passed into that are expected to be objects. But if you pass an integer to that, it gets boxed. And when we are boxing something, that creates a new object on the heap, which is going to be the box. It copies the value type into that object and passes that into the method. And that means you're working then with a copy of the value type, and any changes the method tries to make to that box value doesn't get used. So that's an interesting side effect, and we'll come back to that. One thing that's interesting is that there are some tooling here which can help. So the little screenshot at the bottom there is using a plugin to ReSharper and Rider called the Heap Allocations Viewer. And this will show you and highlight items where things are being boxed where you don't necessarily expect it. So again, like with the params issue, this is something that the compiler and the runtime are doing for you that you don't necessarily see as part of the language. When I talk about reference types and value types, what do I mean here? Let's kind of remind ourselves really what's going on here. So the .NET world, you've basically got two types of two kinds of types, reference types and value types. A reference type uses the class keyword, whereas value types use the struct keyword. References are allocated on the heap, and value types are allocated on the stack. They can also be embedded directly in another object as well. A key difference between the two is that a variable for a reference type is actually a reference to the thing on the heap. So something lives on the heap, and I've got a variable, and it's basically saying it's over there. And when you want to pass things around, you pass it around by that reference. You pass that reference to another method. And both the caller and the called method know that it's pointing to the same thing over here. And when you then assign to a different variable there, that variable gets a copy of the reference and it points to the same object. So you're dealing with the same object. A value type, on the other hand, a value type is the actual value itself. So for an integer, it's just the integer. But if you're talking like a 3D point, x, y, and z, float values, the value type there is those 3 values. So it's not pointing to anything on the heap, it's the actual content of the value itself. This is passed around by value, so if you pass it to another method, it's a copy of it. This is important because then if you make any modifications to that, you're modifying the copy, not the original value. It's also important to know as well, when you're assigning to another variable, you're making another copy. So you might be thinking, if you've got a string, for example, and you have S1 and S2, they're going to be the same string. If you tried to change it, bad example of strings, the same thing, person class, for example, if you tried to change it, both of those variables would be pointing at the same thing and it would change that. Whereas if it was a value type, if you change one variable, the other variable is unaffected. So heap versus stack. I mentioned that reference types are on the heap, value types are on the stack. What's the difference? Well, the heap is it's general purpose memory. It's available there for the lifetime of the application, and it's you allocate something there, and it lasts until it's no longer used. And the garbage collector cleans things up. The stack, though, is a block of memory for data which is required by the method. So when you enter a method, it will push space onto the stack, ready to hold all the data that is being used for that method, for all the local variables. And then when the method exits itself, the stack is popped and everything gets cleaned up. So stack allocation has a different lifetime to the heap. It lasts for the lifetime of the method it's being used in. Value types are the entire set of data. So if you have a value type, which is the point, it's got those x, y, and z in there, that's the whole data. That lives directly on the stack. So straight in the stack there, you've got all of the data for your object, for the thing you're working with. You can also use the stack alloc keyword there as well to allocate blocks of data on the stack. But generally, you don't use that one, and you just use local variables. But what all this means, really, is now that we've got allocation and cleanup being cheap, because everything is just, and lifetime is well defined as well, because it lasts for the lifetime of the method. But you are limited in space. You can't have as big an amount of objects as you can on the heap. All right, back to our list of sort of things we can easily work with. Closures, again, another example of where the compiler rewrites things and introduces allocations for you that are not perhaps very visible in your code. So if you have a closure and you're capturing values and using them inside a lambda, what the compiler is going to do is rewrite that. It introduces a new class, and that class is going to contain all the captured variables or parameters or fields and keep those inside the class. The lambda is then rewritten as a method on that class, so it can use that data and work with it. But now to call that, it has to allocate the class. So you've got an allocation happening there which isn't visible when you look at the code. So LINQ is a great example of all of this. LINQ is very, very useful. It's a great system, but because it's using a lot of closures, it's going to hit this problem, and you're going to have allocations that are going on there. But on top of that, LINQ is based off a lot of static methods which then allocate enumerator classes. So there's extra allocations going on. And again, the heap allocation view, I think, can show this. You can highlight where you've got methods, variables or parameters that are being pulled into a closure class, a display class. And also then when the method itself is going to allocate something to return back to you. Iterators have a similar sort of problem here. So if you've got the yield return type feature in C#, iterators, they also get rewritten as a state machine, and there's an allocation going on there, which the compiler does for you, and you don't necessarily see in your code. A similar thing with async await. Your code is rewritten to a state machine here. There's an allocation for the state machine, there's allocation for the task method builder, and then on top of that, you get more allocations for the task that you return back, your task or your task of T. And this is generally okay, because if you have a long-running process, then you kind of need to be able to return that. You need to be able to return something that is going to fulfill that at some point. But it also doesn't help with some of the common use cases. So if you have a method that is going to complete synchronously rather than asynchronously, so sometimes it needs to go off and do something for a long time, but sometimes it can say, nope, I've got the answer, here it is. It's going to do allocations for those times when a simple method return would have been better. There's also no chance for reusing some of those objects. So when you create a task of T and you give it a value, you can't necessarily reuse that. So it's just kind of like a throwaway item which has been allocated. And the value task type, which has been introduced, is very, very helpful for some of these things. It is a value type which represents the task, and it's great then for some of these use cases where you want to be able to reuse items, where you also want to be able to return synchronously without having to allocate something. And there's a really good blog post explaining some of that there, and I've got some more links then at the end if you want to see those. Okay, so those are our kind of easy things that we can fix up. Those are the sort of well-known things that we can work on to fix up. There's a bunch of ways of working around those. So if we were talking about params, for example, we could introduce different overloads there with a common number of arguments. So perhaps we usually call the method with 2 parameters. Well, create a method with 2 parameters there. You've got the flexibility to call it with more in other places, but if you're frequently calling it with 2, have an overload which does that for you. To work around boxing, you can introduce generic overloads and let the runtime work that for you, so then you don't have any boxing there at all. And if you've got closures, avoid those in critical paths. So if you've got some code which is called very, very frequently or for a long period of time, avoid them, basically. Try and do something different. Perhaps you can pass the state as an argument to the Lambda rather than trying to capture it as a class. One thing which is going to be a nice thing to look at in recent versions of C# are local functions, because local functions have a similar rewriting method going on, but because the scope of the call is known, most of the time the captured data can be represented in a value type. That's then allocated on the stack, which again, as we say, is cheap to allocate, cheap to clean up, and very easy and useful to use. Link, very similar sort of thing there because of the closures there. Avoided in critical paths. We all know how to use for each and if. It might be slightly longer code, but it's going to have a better performance characteristic in something which is called very, very frequently. Iterators is an interesting one. How do you fix an iterator? Perhaps you can allocate a collection and return that. Perhaps that allocation is going to be better than the allocation that the runtime does for you. Perhaps you can't allocate a collection because you've got an infinite stream that's going on there. So you don't really have to know it. And this is one where you kind of just have to be aware of the cost and then figure out a way to minimize that for your particular use case. And then with the sync await, investigate value task. Right, so that's kind of some of the sort of frequently known ways of reducing some of your allocations there. I want to look at something which is a bit more interesting, got a bit more meat to it. And we're going to have a look at reference semantics with value types, which is a bit of a mouthful, but it's all good stuff. It's a set of features that came in with the sort of C#7 compiler and following point releases. And it's a sort of set of building blocks that combine to produce a really nice sort of effect. But what kind of effect? What am I talking about? What does this really mean? Well, if we have a look back at when we talk about reference types and value types, if we talk about allocating a reference type has a cost in terms of garbage collection, but passing around is cheap. I can pass a reference, and it is very cheap to pass around. Allocating a value type is cheap because it lives on the stack, and a lifetime is determined. It can get cleaned up very easily. But then passing it around has a cost because it gets copied. I can't necessarily modify it, and there are sort of costs associated with that. So why can't we just have the best of both worlds? Why can't it be cheap to allocate and cheap to pass around? And that's what reference semantics with value types means. Basically, it allows us to treat value types as though they were reference types. So we can pass by reference anywhere. So we can pass these value types around by reference, and we get all the benefits of everything. So we get to use value types to reduce the amount of allocations we have because everything lives on the stack, and that then reduces our memory traffic, our garbage collections, and so forth, and so on, and that then gives us better throughput. Passing things by reference avoids various copies of these value types there, and it also enables us to modify things as well. So I can instead of passing a copy around, which is a very different thing, and I can't get the information back into it, I can now modify it and work with it. Again, it's important to point out that these are low-level micro-optimizations. You only need to do these in critical paths where you have code that is being used very, very frequently and needs to be very, very fast. But these kinds of things will and are being used in the platform. They'll be used for web servers. They'll be used in games. They'll be used in parsing. They'll be used in serialization. They'll be used in lots of places. You're going to see this. So it is going to happen. You might not necessarily need to use it in your own code, but then again, maybe you do. Again, profile, profile, profile. Right, so what do I mean by pass by reference and pass by value? So I've been talking about these again now. So a variable for a reference type is a reference to the actual object on the heap. So we've got the heap, we've got the thing we're trying to create here, a person, whatever it is, and if I have a variable for a reference type, the variable is basically saying it's over there, it's on the heap. Passing this around is very easy. You just pass a reference to the method. And the called method goes, well, it's that object over there on the heap. It's the same object, it knows where it is, it's cheap, and it's easy. They see the same object. But if we have a variable for a value type, it's the whole value itself. It's our 3 points in a point, the x, y, z in a point. Passing a value type to a method passes the whole thing, and it passes a copy of it. So you've now got 2 copies of the same thing. Assigning a value type to a new value copies the method as well, and the original value is unmodified, so that if you change one, it doesn't change the other. It's also important to point out that copies aren't actually that expensive. It's not that much of a big deal. If I've got X, Y, and Z, it's 3 items, 3 floats, that's fine. It's a little block of memory. Computers are very good at moving little blocks of memory around. So the copies aren't actually that expensive. However, if you're on a critical path, a very hot path, then they can add up. And if you can reduce the amount of work you're doing, then that's great. Okay, so let's have a look at the first sort of building block out of all of this then. C#7 introduced ref returns. And this allows us to return a reference to a value type rather than a copy of the value. So if you have a method and you want to return something back, I want to return my point back from a method, normally it would be a copy of the value. Here I can now return a reference. So that's great. The return type of the method changes here. So here I've got an example of an integer. This now becomes a reference to an integer, written int with an ampersand in IL. And it's very important that the return type of the method changes. If I'm returning back a reference to a value type, then the thing I'm referring to, the thing I'm using, must exceed the lifetime of the called method. So if I have a value type which is a local variable inside the method, I can't pass that back because as soon as I do, the stack disappears for that method and that thing is gone. So that doesn't exist. So I have to pass back something which has got a longer lifetime than the method that has just been called. So this has to be a field or an argument that's been passed in, but not a local variable. For similar reasons, now we can't use this with async methods because obviously async method lifetime all changes and goes a bit funny. So we can't use it for async. What do we got next? The next one, yeah. So if we modify the value, so the value gets returned back as a reference. If we modify that returned reference, then it's the same as modifying the original value because it is the original value. So we're talking about the same thing here. We haven't changed it. We haven't got any copies. We're modifying the same thing. You can do some interesting things with this because I can return now a reference to an element inside an array and modify it in place. So I don't have to call a getter to get the value, set something up, and then call a setter to put it back in there. I can actually just change the actual thing in place because it's a reference, it's the original value, it's the actual thing, there are no copies going on. So there's a lot of very interesting things you can do along those lines. To use this, you need to use the ref modifier and add that to the method declaration, to the return type, and also in the return statement itself. And I'll show you this in a sec. But we've kind of got a problem here now because we've got a method which has got a return type of reference of an integer, int, with the ampersand at the end of it, if you want to talk about IL. And how do I assign that to a local variable? Because a local variable isn't going to be int with an ampersand, it's just going to be int. So If you assign it to, if you assign a ref return back to a new variable, you're going to get a copy, which kind of defeats the purpose, because the variable is a value type, and we've just returned a reference. So C#7 also introduced ref locals, and a ref local is a variable that is a reference to a value type. And again, accessing this variable accesses the original value. They're the same thing. So you use a ref local to restore the return value of a ref return. And you can also use var for this as well, but you can't just use var, you have to use ref var. If you use var, it's going to tell you, well, that's an int, but it's not going to tell you that it's a reference to an int. It's just, you have to give it the ref modifier as well. So let's have a quick look at what this looks like in practice. Okay, so I have a couple of types here. I have a struct, which is a point, two values, an x and a y. They're public, they can be modified, constructed to create them. And then I have my enemy class. And my enemy class contains a point, and it has a constructor then which creates an enemy and gives it a location as a point. I have two methods. One is to get the current location, which just returns it. This is just standard sort of code we would normally write. And here I've got one which is using ref returns. And we can see here now that I've got a ref point that I'm returning back here. So I'm not returning just a point, I'm returning back a reference to a point. And here I'm using return ref as part of my keyword here. So I'm returning back a reference to the item. Now I have some tests. So we're going to do some tests to make sure that the behavior is as we expect. So if we start with the first one, what we're going to see here is we create an instance of the enemy and give it a location at xy 1010. And what we can do here is we can call get location. We get a point back. If I change that value, then I'm actually working on a copy. So nothing changes. So I can assert that my local copy is 12, but then the original value, if I call get location again, is still 10. So I'm working on a copy. That's no good at all. I can call my get location by ref, and this will return me back. This is using the ref return value here, but I'm assigning it to just a point. And so what I get here is a copy, even though I'm calling the method by ref, and I'm calling it with the ref return keywords going on, it's still a copy. I set it to 12, nothing changes, I got 12 and 10 going on there. So what I have to do instead is I have to use the ref keyword when declaring my variable as well. So I have my ref var location item here, which is going to be just a point, but it's a reference to a point. If I change it, location.x is 12, I now confirm that I've actually updated the value which is part of the type. And if we run this, let's just go to the top, we'll see that everything hopefully goes green. So great. Now there's one extra method down the bottom here because you can do some kind of weird things with this. Because it's a reference, I can assign things to a reference and I can do things. So what I can actually do is assign a value to the return value of a method, which is kind of weird. Don't write this in real code because it's just confusing. But yeah, you can do some fun things. Okay, one sec. Yeah. All right. So that's great. We can return back a reference to a value type. We can modify it, and it updates the original value, and that's great, and that's lovely. But the downside of this is that we can now modify someone else's state, which is not necessarily what we wanted to do. So we've got the benefit of being able to return something back by reference, and so we've reduced the number of copies that are going on. But we've now got something which is mutable, and we can mutate state, which we don't necessarily want to do. So we've got then the ref read-only return feature, and this extends the ref returns and ref locals value. Basically, it allows you to return a value type by reference, but the caller is not allowed to modify it. So the way to use this is that you assign to ref read-only var rather than to just ref var, and the compiler enforces this read-only status with errors, compile errors, and also defensive copies. It'll actually make a copy of the code for you, of the value type for you, without you necessarily knowing. So this kind of works around the problem here where I've got some sort of shared state going on. So for example, I might create a point which defines the origin of my game, which is at 0, 0, 0. I want to return that back by reference because that's cheaper and better and nicer. And then someone comes along and modifies that reference. And all of a sudden, I've got really weird bugs happening in my game because somebody has changed where 0, 0, 0 lives. And we can see this in action as well. I've got another class very similar to the last one. I've got a struct point here. Again, we've got public values for x and y. I've introduced a new method here. I've got this translate in place method. And here I can modify the x and y by translating it, adding values onto x, adding values onto y. And I've got two values here for of how we can do origin. So for example, I just create a static point, which is going to be at 0, 0. And I can return it back by reference, like we've just done in the previous example, and work with that. And that's going to be a reference, no copies, everything's great. And I've got my second example here. Let's get rid of that one. Second example here, which is going to be a read-only point now, which again is set to 0, 0. And I've now got a static ref read-only as part of my return type here. And if we look at how we use this, then again, if I just call point.origin, I'm getting inserting it into a standard var, so I don't have any reference stuff going on. I'm getting a copy. If I make any changes to that, then my origin is still fine. Everything's good. That's just like in the previous example. If I call, again now, like in the previous example, I call get the origin back by reference and put it into a reference value, I can change my origin to be 42 in x, and now I've just broken the origin and my game is doing crazy things. So that's not good. So what we do instead then is we introduce this ref read-only var here. So I've got my read-only origin here, and in fact, if I try to assign that to a standard reference variable, I get a compile error. The compiler says that you can't do this. So it has to be a read-only reference, and I need to have the read-only keyword in there. And now because it's read-only, I actually can't set a value on there. So I can't change my origin. The compiler enforces it. So this is great. So now I can pass things back by reference, but I can't modify it. So that's a compile error. And I've got my tests there, which will just verify that everything is fine. But we've now got a bit of another problem again, because you remember I had that method translate in place. So I can actually call a method on my origin, which is read-only, and it's going to translate it in place. And that should change it. So that should change my origin. But it doesn't. The compiler does something for you here. The compiler goes, I don't trust you. You're not necessarily doing the thing you think you're doing here. That's supposed to be read-only, so I'm going to make a copy of this to call this method, because I cannot guarantee that that method does not change this read-only value. And so we actually end up with a copy. And so even though I've set the value to 42 here, I'm still set at 0 at the end. And if we run these tests, we'll see then that all of those assertions hold true, and we're still green on the side there, so all of those are true, and we're still good. But now we've kind of got a problem. Well, actually, I'll come back to that. Next little building block, stepping away from the ref returns just for a sec, is in parameters. So this is a method argument modifier. It kind of complements the out and the ref keyword when you're defining a method's arguments. And it allows you to pass a value type by reference, but you're telling the compiler that you can't modify this. So it's in only, and other than that, you can't do anything with it. And you have a similar thing here. The compiler will enforce a whole bunch of safety, but when it calls a method, it will make a defensive copy. And we can quickly see that one here. Again, we've got our mutable point here now. Just to make the point here, it is mutable. I've got my translate in place, which is going to change things. I've got public value variables there, so it should be changeable. It should be mutable. But now we're going to have, in fact, we can assert that. So if I just create a point there, mutable point, translate in place, it actually does work in it. So we know that that's working. Now, if I have my in parameter here, you can see that I've given this method argument the in parameter marking. We've immediately got a compile error. So you can't do this. You can't modify an in parameter. The compiler says no. So that's great. Compile time safety is even better than runtime safety. However, I'm calling my translate in place, which is going to change things, and I don't have an error, which is not great. So there's something happening there which I don't necessarily want, and I've just uncommented a comment. So let's see what's going on. Let's have a look. What I can do here is I can create a new instance of my point, pass it into this doTranslate method here, and that doTranslate is going to have the in modifier. So we're now saying that this particular value type is going to be read-only because it's an in parameter. I can call the translate in place, and then I can assert it, and it's going to tell me that actually that doesn't work because it's actually reset it back to 10. I originally set it 10 in the first place there. So the translate doesn't work. What the compiler does, again, is create a defensive copy for you. So that's great. It's kept it read-only. It's kept it fine, but we've got another copy going on. And interestingly, you could then try, well, perhaps I can cheat. Perhaps I can pass that in parameter in as a ref, so then it becomes in, out, and modifiable and all that. And fortunately, the compiler's thought of that, and it doesn't like it, and it gives you a compile time error. So you can't do that. And now if we run these tests, we'll see that all those assumptions are also true, and we're still green. Did that run? Yep, there they are. So we're still green there, and everything we've tried to do so far is good. But that gives us a bit of a problem, because we're trying to do all these things to pass things around by reference, and it's working, it's great. We've got a whole bunch of compile time errors, which is useful. But if I call a method on it, I'm getting a defensive copy. And it's like, well, how do I stop that? How do I, I want to try and avoid some of these copies happening. How do I avoid that? And there's another feature, another little building block, which we've got here, which is the read-only struct. And this is to tell the compiler, basically, that this structure is read-only. It's safe to call methods on it because calling a method is not going to modify the state. It's not going to mutate the value type itself. So that makes the type itself immutable, and this is great because now there's going to be no copies being made anywhere. We can pass things around by reference. We can call methods on it. We can have compile time errors, and basically we've now got the best of both worlds. And if we have a quick look at this one, we've got a read-only struct. Again, I've got my point class here, but I've added the read-only keyword to the definition. So it's now a read-only struct of point. And now the compiler is going to enforce security here. So if I have a mutable type here, a mutable value here, the compiler gives me a warning. It tells me that you can't do this. It has to be immutable. So we need read-only going on there. And that's great because now I actually can't even write my translate in place code because I get errors. The compiler enforces this because it's read-only. It's immutable. So that problem goes away. And if we have our value here where we try and get our points, so I've got the point going on here again, read-only reference types being returned back. And if I try and use it, even if I assign it into a copy there, I try and assign something to it, I can't, it's read-only, it's immutable. We get compile errors. And even with a reference read-only reference, sorry, it's using the same object, but it's read-only and it's immutable. I get compile time errors. And if I try and call a method on that, well, I can't even define the method because it's immutable. So it's no good. So it's not even worth running those tests because I can't compile. So this is great, more efficient, got no copies made when calling members. We can pass things around without calling members. And this is great for throughput, performance, and so on. But again, these are all sort of micro optimizations. But they can add up in critical code paths. The other key thing here is that there are no changes to the CLR. So all of these features have been added just to the language. This has been previously supported by the CLR all along, and now it's just exposed by C#. So we can make use of this anywhere and everywhere. All right, one last building block, which is really useful here. This is one which looks odd on the face of it, but is really useful, and we'll come back to it shortly. This is a ref struct. This is the ability to declare a value type that can only be stack allocated. You can't allocate it anywhere else. You can't embed it as part of another object. So you couldn't have a person which contains one of these ref structs. And you can only allocate it on the stack. So this constrains the lifetime of these value types. It also means they can't be boxed. They can't use them inside another struct if that struct is not also a ref struct. You can't use it with async methods or iterators. Can't be used as generic parameters. There's a whole bunch of limitations to it. It doesn't really kind of make sense as to why you would do that. And so there are very limited use cases for this. So one of which is using stack alloc, and that's just a way of allocating a block of memory on your stack. But the big reason is for Span&lt, which is a new type which has been around. It's actually been around for a little while, but it's a very useful type which is all about reducing the amount of allocations you get. And this is where things start to get useful for you as an application developer. So Span&lt is it's a new type, really, to unify working with any kind of contiguous memory, any block of memory. So if you've got like a nice big block of memory like an array or a string, which is using one long self-contained block of memory, is really useful for working with that. Also useful for working with array segments, so chunks of an array, or substrings. Also good for native memory and for memory allocated on the stack with the stack alloc keyword. And basically, it provides an array-like API for working with this, this block of memory. So it looks like indexes, basically. You've got a get and a set. You've got the indexer with the square brackets. You've got get and set methods and so on. And there's also a read-only Span&lt type, which is read-only, and you've only got getters. It's also type-safe. So each element in this array, this block of memory, which you're going to start treating like an array, is type-safe. It is an instance of T. So if you have a span of byte, then each element in there is going to be a byte. If you have a span of point, each element of that is going to be a point structure. And the nice thing about this is that you get array-like performance. So it's not quite as fast as an array, but it's really close. And the newer runtimes have special support built into this to make it really close. So it's very good. This is a great way of working with blocks of memory like arrays and have the same sort of performance and APIs as arrays. But one of the key things, one of the really, really useful things with Span&lt is slicing. You can create a new span of T, which is a subsection of an existing span. So if you're talking like you've got a block of memory which is going to be a string, you can get a substring out of that by pulling out a span which is just that section there. And all of this is without allocations. So if we're saying that it's without allocations, that means it's a value type. Yes, it is. It's great. It's available as a NuGet package for .NET Standard 1.1, which means .NET Framework 4.5 and above. It's built into the, I've lost track if it's built into the .NET Standard. It's built into .NET Core 2.1 and above. I think it's in the standard. I forget now. But there's also a whole load of new APIs and overloads for working with span. So you can convert a string to a span, or you can have streams that return, instead of returning a block of an array of bytes, you can return a span. And also then for parsing blocks of text. So UTF-8 parser, converting a string into UTF-8 text. And the whole point of this is that it makes huge amount of use of all the ref semantic stuff we've just been talking about to get a whole load of allocation-free stuff going through. And it's really a handful of types. You've got Span&lt, read-only Span&lt, which I've already mentioned. There's also memory of T, which is an interesting one. It allows you to work with work around the limitations of Span&lt being a struct. And I'll talk a bit more about that in a sec. There are also two versions. So on more down-level versions of the .NET Framework, then there's a portable version, and then there is effectively a fast version. The fast version requires runtime support, but it's kind of important to say, really, that the portable version is not slow. you get, it's not as fast as arrays, but it's still good. So it's, just because it's portable doesn't mean it's slow. So this works on .NET Framework 4.5 and above as part of the .NET Standard 1.1, which is old now, and with .NET Core 3 and .NET 5 could mean anything. But the implementation of this one really is that this span of T has 3 fields. You have the object reference to the big block of memory. You have an internal offset for where it starts, and then the length, so you know where it is there. So this is actually slightly larger than the fast version, but the difference is slightly there. So dereferencing values is slightly more complex because you've got to go to the start, add on the offset, and then work with that, but that's fine and easy. The fast implementation requires runtime support, and this is .NET Core 2.1 and above, and the runtime recognizes this type. This only has 2 fields. It has a special by-ref internal pointer. So you've got this block of memory, and the span says, I start there. So it doesn't have to start at the beginning and count. It knows exactly where to start, and it knows the length, which means getting at the values is slightly faster and slightly simpler, and therefore slightly better performance. But more importantly, the runtime knows this type, and it has specific optimizations in the JIT to get rid of a few things in the same way it does with arrays. So for example, when working with arrays, the runtime, the .NET Framework runtime, .NET Core runtime, recognizes that you're iterating over an array, and it gets rid of the bounds checks for each array access. So it knows you're going from 1 to 10, and it doesn't have to do a bounds check on every single one of those. The runtime can do the same thing for span of T, and that then gives you very, very close to array-like performance. So what does this have to do with ref structs? So I was talking about that, and I was building blocks and all this. Where does all that fit in? Well, because we've got these fields inside the span of T, we kind of have to update everything all at once for thread safety. So we have to do it all sort of atomically. If we only did one part of the thing without doing the other, it would break or be horrible and nasty. And the whole point of this type is performance, so we can't put locks and synchronization around it there because that defeats the purpose. There are other reasons as well, is that this by-ref pointer into the middle of an object requires special tracking inside the garbage collector. Having too many of those on the go at any time can get expensive, but if you reduce the amount of them, then it's manageable. Also, if you want span of T to allocate, to represent a whole bunch of different types of memory, from strings to arrays to native memory to stack allocated memory, how does it deal with stack allocated memory if span of T was a class and lived on the heap, because stack allocated memory only has a constrained lifetime? And the answer to all of those questions really is that span of T is a ref struct. And by putting all those constraints which we had for ref structs on span of T, you fix all of those problems. It can only be created on the stack, so you don't have to worry about thread safety anymore, because on the stack it can only be called from one method. You can't pass it around because it's got constrained access. You don't have to worry about the number of garbage collector handles going on there as well, because you're only going to have a limited number of those thanks to the core stack. Okay, so let's have a quick look at this. So I have another set of tests here of using this. Now I've got this added as a NuGet package. So I've got my packages there. I have oh no, sorry, I'm using this as a .NET Core app. I forgot. Yeah, so it's .NET Core app, so it's part of the .NET Core API itself, and so I'm just using that, and I get to use myString.asSpan. So I've got an extension method here, which is going to convert myString, which is a constant defined at the top of the class there, convert it into a span, and I assign it here now to a read-only span of char. And from here, I can do a bunch of things that you would normally expect to do with strings, basically. I can treat it in the same way. I can check that the span's length is correct. I can do equality with another string. So I can do string comparisons based on this span, comparing it to another string. And I can do that string comparison with the same sort of invariant culture, ignoring case, and so on, because thanks to these extension methods. I can even do things like starts with, make sure that it starts with the appropriate values. I've got another test now which will create a slice. So again, one of the benefits of having span, in fact, the best benefit of it is being able to slice and pull data out without having to allocate anything. And so if I call slice of 6 there, I can then confirm with a call to equals that I've actually got a value here, which is what I would expect. And I can do a similar sort of thing here with arrays as well. So I have my numbers array at the top here. It's just a set of arrays of 1 to 10. I can create a span out of that. I don't have to call as span here. There's an implicit conversion. So that's nice. I can just treat an array as a span without having to do anything. I can then slice it. I can start at 3 and go for length of 5. And if I change that element there inside my slice, I can then confirm that actually it's going to be this value here inside the main array. And so if I run these tests, we should see then that, again, those assumptions all go green. And then the best thing is that it's all allocation free as well. So I've got another test here, which is, first of all, getting the current amount of memory. I then make sure that I'm not allowed to do any garbage collection inside this area. I call all of those tests explicitly, and then I just assert that 0 memory was allocated there. There was no change there. I changed there. So this is kind of like a very crude way of checking to see that there's no allocations happening at that point. And so we can see now that we can do all of these things, create slices, and change values and all of that without allocating any extra memory. All right, so that's great. Span&lt is really useful, and I can probably see a number of useful ways of doing that. What about sort of real-world usages from something else? Very handily, a couple of days ago, Microsoft announced a preview of SystemTextJason. This is a new library which they're using, which they're introducing to do JSON serialization and deserialization for the .NET platform. This is to effectively decouple JSON.NET from the platform. Because the problem is the platform currently relies on JSON.NET, and it relies on a particular version of JSON.NET, which means that you can't update it without updating your platform, and your application versions mismatch, and so there's problems there. They also want something which is better from a performance point of view, making use of some of these new APIs, and so basically they've introduced a new library. So the whole point of this is that it uses, as part of what it does, it uses Span&lt to be able to work with things, be able to parse things without having to introduce a whole load of new allocations. And it's optimized for the things you'd expect to use JSON for in real life, in web servers. And generally you work with UTF-8 rather than UTF-16, which is the actual encoding that the string type uses. And so normally you would have to read everything in, convert it to UTF-16, and work on that. But what system.text.json can do is read in a set of bytes from the file, treat those as UTF-8, write over by putting it all into one big span, and work with that span to parse things and match things and get data without allocating anything, without having to allocate any strings. This is going to be part of .NET Core 3, and right now there is a preview NuGet package which you can download and try and use. The blog post which they have has some micro benchmarks against JSON.NET. And you can see here now where these kinds of things can start to really pay off. So in the benchmarks that they've used there, so deserialization can be 2 times faster because of reduced sort of, better throughput, basically. Serialization can also be faster. But getting at the document, using the document object model, writing and reading, these can actually be more or less allocation free. And the more or less is because the way that they've implemented things is that there are some allocations happening. So for example, when you read data in, you have to put it into a byte array, but some of these things are pooled, an object pooled. So if you ignore the overhead of those pools for the object arrays, the byte arrays, then you don't get any actual allocations for the objects themselves until you then try. So for example, you read it, you want to get a string value out, that will then allocate you a string. And again, you can see now where this throughput really helps with, again, from the blog post from from the other day, talking about JSON deserialization and serialization. You can see the requests per second figures for the difference between JSON.NET and SystemTextJason. You're actually getting real-world improvements there. You're getting better requests per responses per second. Memory usage is not so dramatically different, but the actual the throughput itself is. And we can have a very quick look at something here. So if we have a little bit of code here, for example, we can parse the value here. If we pass in a string, we can parse that and pull that out into a JSON document. So now kind of like got a DOM value here. I can then have, that will allocate. That's going to allocate my byte array to read the values. It's going to have some allocations going on there. Those allocations are pooled. So we're making use of sort of the object reuse, which we were talking previously with the low-hanging fruit stuff. But now if I wanted to enumerate that object model, I can use this enumerate array value and have a look at how that works. If I go to the type of that, we can see that, let me do that again, sorry. So if we go to enumerate array, we see that that returns back an array enumerator, which is a struct. So this is great. I'm going to return back an enumerator, which is a struct, so there's not going to be much allocations going on there. And if we have a look at JSON element here, we see that that is also a struct. So we're working with value types and we're avoiding allocations going on here. If I very quickly step into get property and try get property, we then see that we're converting this into a span. So we get looking for a particular property with a name, which is a string. We convert that into a span. And when we pass this in here, let's see if we can find the right bit of code. Nope, that's the wrong bit of code. We're working with spans there, so we get to use the spans going on internally. If we have a look at the getting an integer, and if we step into that a couple of times, that calls get, which finally calls this, we can see here that what we're doing to get the actual value is that we are finding out where this particular property lives with a location and a length, and then we use a slice on the original string that we've got to get that particular bit of text there. So we're using slices to get at the value, which we can then decode and return back. And because this is returning back an integer value, then we're going to be able to do all of that without allocating anything, which is pretty nifty. So yes, so that entire loop there won't allocate anything, which is very nice. So I can work with a document object model without allocations. Which brings me to the end. So then that really is everything that I wanted to show you. There's reasons for wanting to reduce the number of allocations we do is all about throughput, all about reducing the amount of memory we're using, the amount of memory traffic that's happening, so that we can reduce the number of garbage collections, improve throughput, and hopefully then that will improve performance for us as well. Key thing is profiling. These are all micro-optimizations, but they can have a very big impact, as we saw with the benchmarks there for the responses per second. And there are a number of ways of doing this. We obviously look at some of the low-hanging fruit there, but there's also a number of interesting building blocks with value types, passing those around by reference, and being able to enforce safety of making them immutable, and so we can't change them, and working with that code there. And finally, Span&lt. Span&lt is really, really useful and something that you are likely to use in your own code if you need to do any kind of parsing or serialization yourself, and to be able to get data there without having to allocate anything. These are some very useful links which have details about it there. So the first one is Microsoft's documentation for these features, which explains what's going on with the reference semantics. More detail about the Span&lt, some really good sort of blog post there explaining how Span&lt works, how the runtime has optimizations for it. And then also there's a great post on how value task works and when and why you would want to use it there. There are some really good use cases for avoiding allocating task and task of T and using value task instead. And then finally, there's the SystemTextJason blog post from a few days ago there, which is describing this new API and some of the details around that. And finally, if you want to get some of the tests that I was running today, the sample code there, it's up on GitHub in the top right-hand corner. I think probably out of time there. If anybody has any questions, please feel free to come down and ask. I'll also be at the JetBrains booth, so if you want to pop by and say hello, then feel free. And please don't forget about the feedback cards on the way out. Other than that, thank you very much.